Hey guys, today I'm just going to go over some code that I wrote to test the pulse width modulation mode of the CCP2 module on my PIC18F 45K20. Still learning, of course, so if you have any suggestions, or if I don't understand something properly and you do and you want to correct me, then please feel free. So let's get right into it. You know, I got my little title block and my list and include, my configure settings. Don't necessarily need all of this, but I do it anyway. And I'm going to start my code at hex 00, which will go here to some initial settings that I like to set up. So the first thing I'll do is set the oscillator to the desired frequency. I called out to use the high frequency internal oscillator block of the PIC itself. So if we want to look and see what this hex 66 means, then we can look at the data sheet and go down to the oscillator control register section here, and we'll see that we've got a 0, which means the device enters sleep mode on the sleep instruction. I could put a 1 there. It doesn't matter. We're not going to give it a sleep instruction. And then we have a 110. So if we look here, 110 means that I've set it up to 8 megahertz. And then we have another 0110. So the first 0 here is device is running from the internal oscillator. The first 1 means that we've selected the high frequency internal oscillator frequency bit to be stable. And the last 1 is the internal oscillator block. That's where the system clock is going to be, that's where the system's going to get its clock from. So, and then I put a 0 because the X here is a don't care condition, which Microtrip has pretty much designated it that it's going to be a 0 anyway. So that's that. Now let's go back here and we'll see what I did. I've disabled comparator 1 and comparator 2. Not really using them. So, and in here I've just cleared port A of whatever's sitting on the inputs, and I've made it all digital outputs by clearing the lat A register and the tris A register. And I've done the same thing with port C. I did make another note here saying that I enabled the CCP2 output driver for the pulse width modulation, which basically just means it's set to an output. Then here I'm setting up my CCP2 control register. The bits 5 and 4 of the CCP2 con register are the 2 least significant bits for the CCP2 duty cycle in pulse width modulation mode. So I've selected 3 here just arbitrarily, so they're both set high. And then the last 4 bits, which I've got the C, which I believe is binary 1100. If we look at the CCP2 con register, see if we can find it here. Okay, so once we get there we go. Bits 3 through 0. These are the CCP2 mode select bits. And so if you go all the way down here, you'll see that 110 is pulse width modulation mode, which is why I've selected that. So now the next thing I've done here is just loaded an arbitrary value into the working register to move into the CCPR2L register, which is the 8 most significant bits of the pulse width modulation duty cycle. Now the way this works is that in pulse width modulation mode, CCPR2H is not used. I think you can read it, but it's not used. So that's why the two least significant bits are up here in the CCP2 con register. So bits 9 through 2 of the pulse width modulation duty cycle will be found here in CCPR2L. So if I want to set the duty cycle to 0, then I can just clear this register and clear the clear bits 5 and 4 of the CCP2 con register. Likewise, if I wanted 100% duty cycle, or as close as you can get anyway, which would be 99%, 99 point something, then I could keep these two bits high, bits 5 and 4, and set all the bits high in the CCPR2L register. And then if I wanted a 50%, well then, let's see, if we got a 10-bit, we have a 10-bit pulse width modulation, which means we've got 1024 possibilities, because that's 2 to the 10, right? So if we wanted 50% duty cycle, then we would select half of that, so 512. So that means we would just set bit 10 high and everything else clear, and that would give us 50%. So when we go to when I cut to the video and show you the trace on the O-scope, we'll go through those. You know, we'll start by loading this arbitrary value here, see what that gives us, and then we'll set them all to 0 and see if that does give us a 0%, and then we'll set them all to high, see if that gives us 100%, and then, you know, we'll set bit 10 high and everything else low and see if that gives us 50%. So the last thing I've done as far as like real code, because you'll see in the main program there's nothing, we're just going to sit here forever. There's nothing else that I want to do with this code, so we'll just loop here continuously after we've set it all up. And then to change it, you know, I'll just come in here and change the values and then remake and build the program onto the PIC. So we'll never get to the end to say bye-bye, but that's okay because we don't want to. So the first thing I've done is cleared the interrupt flag for the timer 2, which I always do before I do anything to a timer. And then I cleared this T2 CKPS1 bit, which really I didn't need to do because it should be cleared by default. And really, if I did it like this, then I should clear the T2 CKPS0 bit, which is this is the timer 2 clock prescaler select bits basically. So if we look for the T2 con, then we should be able to determine what I've set up here. Here we go, T2 con. Alright, so the T2 CKPS 1 and 0, timer 2 clock prescale select bits. So if I've got 0, 0, which I do, then I have a prescaler of 1. And the last thing I've done is turned it on. So you'll see, let's see what bit that is. T2 on would be bit 2. So I could have just loaded the hex value, what is that, 0, 1, 2, 3, 4 into the working register and then moved it, but this did just fine. So that's the program in a nutshell. I'm sure you can see what it does. It's pretty simple. I was surprised how easy it was to set up, being that I'm new and new at programming PICs, and I think that there's room for improvement, of course. You know, there may be an easier way to do all of this. There may be a prettier way to do it all. Who knows? Anyway, as always, like it, hate it, share it, you know, subscribe, send me hate mail, you know. No, seriously, I welcome your feedback. You know, if you want to see more like this, let me know. If you've got suggestions of how I can make this better, let me know. And when I say this, I mean, you know, videos like this that I do, you know. So that's pretty much it. I'm going to go ahead and cut to the video now, and we'll check this out on the scope and see how it looks. All right, thanks for watching. All right, guys, so I've got the PIC18F plugged into the computer and plugged into my little demo board here with the 18F 45K20. I've got my probe on RC1, which is the pulse width modulation output there of the CCP2 module. And of course I got my batteries powering everything. And so here's the scope. And let's go ahead and zoom in on that. And let it adjust. I'm getting a little... Let's go a little further so we know that you can see the duty cycle. Alright. So right now the duty cycle is sitting at about 71%, it looks like. 70 to 71. And that's with that arbitrary value that I had in there, which was the B53. So if we want to go to 0%, then we'll go ahead and we'll change everything to a 0. And we'll just clear it all out. And we'll make and build the project. And once it finishes, it'll erase the PIC and then program it. We should see it drop to 0. And there it goes. You know, it doesn't really give us a duty cycle or a frequency because there isn't one. So now let's do 100%. So what we'll do is we'll go up here and we'll set all 10 bits high. So that'll be FF3. And we'll go ahead and make and build that. And see what we get. It's about to happen. There we go. You can see it jumped up. And we're sitting at 99.22% duty cycle. So now let's say we want 50%. So for 50%, we know that we need to set a value of 512 decimal, which would equate to basically a hexadecimal number of 800. So that will set the 10th bit, or bit 9 if you will, of the pulse width modulation duty cycle select. It'll set that bit and everything else will be cleared, and we'll go ahead and make and build it, and we should get 50%. And there you have it. 50% on the nose. So that's cool, right? But who wants to sit here and change the values all the time? So now I'm going to figure out how to use the analog to digital converter and the analog input on RA0 along with the pot. Let's zoom out, go down here. Okay, so if we can set up the analog to digital converter, we can use this potentiometer here to adjust the voltage present on the analog input on RA0, and that will give us a value that will then move into the pulse width modulation, and that's how we'll adjust it. So I'm going to figure that out, and when I do, I'll post the video. So thanks for watching.